10.4 has to do with probability distributions, and it always starts out with the best question. What's that? What is a probability distribution? Is, first of all, is a list of all outcomes. So you have your experiment, and you're going to list every single thing that could possibly happen. We'll do that in just a sec. But then you're going to pair it paired with each one's probability. Okay, so you're going to list everything that can have it, and then you're going to pair it up with its probability. To save us some time, I'm not going to get into this, but we can do this both with probability, which is theory, what should happen. Like in theory, if you flip a coin, half of them should be heads and half will be tails. If you actually do the experiment, well, that might not be the case. So relative frequency is, that second one is based on an experiment where you actually do the experiment and see what results you get. So for right now, we're going to talk about a probability distribution. We're going to talk about the theory behind what should happen. And then if you want, you guys can do an experiment and see what really will happen. Okay, so let's talk about the experiment of throwing 2 dice and adding them up. Now, I attached a dice paper with you, and it's got a list of all the different things that can happen when you throw 2 dice. It's on here 4 times. You obviously only need it 1 time, so if you want to cut it out, you can. But here's all the different things that could happen. Okay, so you might throw a 1 and a 1, 1 and 2. You get the idea. So if we're going to add them up, the very smallest sum you could possibly have is a 2. If we're going to add them up, the very biggest sum you can possibly have is a 12. So that's going to go over here. And then obviously you can get every sum in between. So 3, 4, 5, 6, 7, 8, 9, 10, and 11. So what we just did is we just listed every single outcome that could possibly happen in this experiment. Everything 2 through 12. Now what we're going to do is say, all right, what's the probability that each one of these happens? You might say, well, they all have the same probability, exactly the same probability you throw each one. Well, let's hold on one sec. When you find probability, on the bottom half of the probability, always you're going to put the total number of possible things that could happen. So these are going to be fractions all the way through. Some of these fractions can be reduced, but I'm just going to not, to save a little bit of time. Okay, so how many total options are there? Well, look at, these are all the pairs, and I see 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. I see a 6 by 6 rectangle or square here. So that means that there's 36 possible things that could happen. Each one gets a 36. Now the numerator is going to be the number of ways you can do each thing. So how many ways can we get a sum of 2? Well, there's just 1. So there is a 1/36 probability that you will throw the dice and they'll add up to 2. How about a 3? Well, the convenient thing about this little chart is that your sums work in diagonals. So your sums of 3 right here, there's 2 of them. And how about we fill out this table kind of twice as we go, or we can fill it out from both ways, because if I notice right here, there's only one way to get a sum of 12. So we can fill that out over here. And then for an 11, there's 2 ways that you can throw it and add up and get a 11. So 2. You could probably even see what's happening now is that when it comes to a sum of 4, there's 1, 2, 3 ways. 4, 3, 4, 5, 5. And then the highest probability is a 7. Which is why, if you've ever played the Settlers of Catan, the robber gets the 7, and the reason is because that is the highest probability. In theory, 1 out of 6, 6 out of 36, or 1 out of 6 should be thrown a 7. Now you know that you've got a probability distribution. If you take all of these up, they should sum to 1. They should add up to 1. If they don't, you don't have a probability distribution. So I think there's some problems in the book that say, is this a probability distribution? They're just asking you, do all these probabilities add up to 1? Because you have to have a list of every single thing that could possibly happen. All right, now how about this? How about if we rolled the dice a ton of times and we rolled the dice, add them up, write it down. Rolled the dice, add them up. And we do this, I don't know, 1,000 times, 2,000 times, something like that. And then we took an average of all the sums. Well, what could we expect? What would be your expected average for all of these? Well, we're going to talk about that in just a second. I'll answer that question. You might say, hey, I expect something in the middle, and you're probably right. But let's check it out. All right, if it asks you to graph these, nothing too complicated here. Over here, we're just going to put all the different outcomes. So we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So here you're going to put your outcomes. And then over here, you're going to put your probability of each one. And if you notice the absolute highest probability, we're going to make our scale 36 is going to be 636. So we can go 1, 2, 3, 4, 5. That's going to be 536 and then 636. And now we're just going to graph it just like XY graphing. So the probability here of getting a 0 is 0. The probability of getting a 1 is 0. The probability of getting a 2 is going to be 136, 236, 336, 4, 5, and the very tallest one is up at 6. That's where your 7 is, and then back down. And then obviously anything over a 12 is going to be back down to 0 all the way through. So that's how you can graph a probability distribution. You'll very often get this little pyramid triangle looking shape. All right, the last thing on this video then is expected value, or the mean of the distribution. Okay, so the way that you find it is exactly what I said before. What would be the expected value? Would be what would be the average if we rolled the dice a ton of times, added them up, and then took the average. Well, here's how you would do it. What you would do is you take each outcome and you'd list it. Okay, so we would call that XI. Those are your outcomes. So we're gonna list them, and so your outcomes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you'd make a list. And then you'd multiply it by its probability. So you'd have the probability of XI. So this 2, there's a 1/36th probability. We're going to multiply each one by its probability. It's going to get tedious, so I'm going to stop writing them, but you get the idea. You're going to match each outcome with its probability. When you're done, you're going to add them up. So that sum right there means add them up. I equals 1 to n. So you're going to have the sum of each outcome matched with its probability. So this is a good time to hop on the calculator. We're going to go like this. We're going to go 2 times its probability plus 3 times its probability. Oops. I'm going to flip back here just so I can see my outcomes and my probability. Plus 4 times 3 divided by 36 plus 5 times 4. 6. Now the big thing here is just to make sure I don't mess up. Plus 6 times 5 plus 7. So if you can see what I'm doing here, I'm taking each outcome, and multiplying by its probability. Go ahead and hit enter. Boom, you get 7. That makes sense because that number is right in the middle. It won't always be smack dab in the middle. But this one is a nice symmetrical one. So here's what that means. It means if I do this experiment a lot and then take the average of my results, we can expect the average to be a 7. Doesn't mean it will be, but that's what we would expect. Okay? So the mode is the one that's most probable in this case. the one that's most probable. So if I'm looking at this, at my results, the mode, the one that's most probable, is going to be equal to a 7. All right, this was a nice, easy one. Let's try one that's a little bit harder. Okay, suppose a lottery pays $8,000 to someone who correctly guesses a series of 4 numbers. The numbers are 0 through 9. With replacement, that means that if you guess the number 1, you can guess the number 1 again. What is the expected value or the average earning for someone who plays the lottery and it's free? Okay, how does it change if the lottery costs $1? All right, well, first of all, let's see what we can expect per ticket. Okay, so we're going to take each outcome that you could possibly have, and the 2 outcomes would be this, would be that you win $0, and then the other outcome would be that you win $8,000. Those are the 2 things that can happen. Okay, now we have to find what's the probability that you win 0 and what's the probability you win 8,000. Those are the 2 things that can happen. Okay, so if we're guessing numbers, let's guess the first number. How many different numbers could we guess? Well, 0 through 9, there's 10 different numbers. With replacement means that we can use those numbers again. So there's 10 different numbers that are here. On the second one, how many different numbers could we choose? Once again, that's going to be a 10. Third one is a 10. Fourth one's a 10. So in all, if I go 10 times 10 times 10 times 10, I believe that's 10,000. There's 10,000 different tickets, or different, not really tickets, but 2 different options that could be selected. So only one of those is the winner. So the probability that you win is 1 out of 10,000. So the probability you win $8,000 is $8,000 is 1 out of 10,000. The probability you win nothing is 9,999 out of 10,000. So what we just did is we listed each outcome, winning 0 and winning 8,000, and we paired it up with its probability. So right here, the probability you win 0, we don't really need to do that math. Multiplying by 0 does nothing. So we're going to go 8,000 times 1 divided by 10,000, and we're going to get 80 cents. 0.8 or 80 cents. A couple different ways to think of that. What that means is, in this case, if you bought all the tickets, you would win 80 cents per ticket. But that's what we're going to call the expected value, meaning if all these tickets sell out and we added up everyone's winnings, what would be the average amount of winnings? All right, let's answer the second one. How does the problem change if the lottery costs $1? Well, now you don't win $0, you win negative $1. You lose everything, and you lose $1. And then for the second one, you don't win $8,000, you win $799 because you had to pay $1 in order to do it. So anytime the problem has a cost, you have to adjust what your 2 outcomes are going to be. The probabilities don't change. There's still a 1 in 10,000 chance that you win, and there's still a 9,999 out of 10,000 chance that you don't. So now, but our math is going to be slightly different. We're going to go negative 1 times 9,999 divided by 10,000 plus 7,999 times 1 divided by 10. 1, 2, 3. And we get negative 0.2. Meaning, in this one, if you bought all the tickets, you would lose 20 cents per ticket. Another way to think of it is if we took all of the winnings and losings and we added them up and took an average, what would be the average amount of winnings and losings? Well, the average person on average would lose 20 cents per ticket. So in the first one, if you're running the lottery, you're going to lose. In this one, you'll for sure make some money.